It's my pleasure to introduce Karianne Bergen. Karianne is a postdoctoral fellow at Harvard's University Data Science Initiative, and she's also a visiting assistant prof at the Department of Earth, Environmental, and Planetary Sciences at Brown University, and soon to be not just visiting, to be there permanently. Karianne received her MS and PhD in computational and mathematical engineering from Stanford, and her BS in applied mathematics from Brown University. Dr. Bergen focuses her research on machine learning and discovery in large and noisy data sets, focusing on earthquake seismology and biodefense. It's my pleasure to have her present today on the topic of DAS and big science data analysis. Karianne?
All right, thank you. Thanks, everyone. All right, so thanks everyone for being here virtually, and thanks to the workshop organizers for inviting me to speak today. So as was mentioned in the introduction, my background is in data science and computing, and I spent a lot of time thinking about how to analyze large data sets for earthquake seismology, but like many of you who are attending the workshop, I'm new to DAS and DAS data. And so today I'm going to share with you my perspective as someone who's interested in data science and interested in machine learning on what makes DAS data challenging, but also potentially interesting from a data science perspective. So normally when I'm giving a research talk early on, I'll have sort of a big data slide like this one, where I talk about sort of two dimensions of big data in seismology. One being long duration data sets. These are data sets that we call large T data that represent years of continuous data collection. This has been the focus of my work in the past. And then also large N data sets, which are large sensor arrays that may contain thousands of sensors or channels. So usually in this sort of a slide, I would throw DAS in as an example of an emerging source of large N data, and then sort of go on to emphasize the need for scalable algorithms. But as I was reflecting on this for this talk about DAS for this workshop, I think it's not quite right to look at this as a large T or large N. It's more useful to sort of map out these data sets in two dimensions. So we have what I've been calling large T data sets. These are data sets from regional seismic arrays. They tend to have longer duration, but more modest number of instruments, so say tens to hundreds. And then on the other hand, you might have dense nodal arrays, which may have thousands of sensors, but would typically be shorter deployments. They wouldn't be in operation generally for years or decades, like you might see with a regional instrument. And so although we can have big data sets that are sort of on the extreme end of large T or large N, with DAS, we have the potential in some sense to have both. So these are large N arrays, potentially very large N arrays, that over time are going to grow also into large T arrays as well. So this space where we have both large N, very large N data that also gets to be longer time durations, I think this is going to be a really interesting challenge moving forward from a data science perspective. And so there's several characteristics that make analyzing big data sets, like data from DAS arrays, more difficult or complex than standard data analysis. This is where we get sort of this big data buzzword coming from. And so there are several ways of characterizing these big data sets that I think are useful for thinking about for DAS. So one is the volume of big data. And so that's the amount of data that's being accumulated. And for DAS, this is very large. You may get 100 gigabytes to 10 terabytes per day with a single DAS array. This is sort of the order of magnitude of data you might be collecting. And so for data sets this large, scalability is really important. And we really need algorithms to extract information from these large raw data sets. 100 gigabytes of data, 10 terabytes of data is too much for a scientist to sift through themselves. So we need automated analysis and algorithms that are really going to scale to be able to be applied to these very large data sets. Another aspect of DAS data that can be challenging is what's called velocity, the need for near real-time analysis of DAS data. And this is something that comes up with applications like urban hazard assessment, or as we saw in the previous talk, potentially earthquake early warning type applications, where you need to be able to get results very quickly in near real time. And so this is challenging, one, because you need to analyze data very quickly with streaming data and streaming algorithms. And the other is that your algorithms need to be fully automated. You don't have time like you would in an offline setting to have a scientist who can sort of configure the algorithm and tweak it to make it work better. Everything needs to be fully automated and able to run very rapidly. So this is relevant in particular for DAS for some of the applications we've talked about. There's also Another characteristic that makes analyzing big data sets challenging is variety. So this can refer to having multiple data sources, multiple data types, or data from multiple instruments. And so, DAS isn't a single thing. There are a range of different kinds of DAS systems. There's variation across them and across DAS deployments. And there's also a need to combine DAS data with other more traditional seismic instruments like seismometers or geophones. And so we need algorithms that can do this kind of sensor fusion, combining DAS with other sources of data. There's also sort of the final V. These are the 5 V's of big data that you hear about. The final one is what's called the veracity of data, or the data quality or uncertainty of data sets that can make them very hard to analyze. And so this is something that comes up with DAS in terms of the data quality. In particular, the cables are often in noisy urban environments. There can be poor coupling, which is something that's been mentioned before. And so these are much messier data sets than what you would typically see from a standard sort of purpose-built scientific instrument. So we need methods that are going to help automatically clean the data, do quality control, and potentially do some denoising of the data. And so even though I sort of present these as challenges, there's another challenge that isn't really reflected in these kind of typical framework for big data, which is the novelty of DAS data, which I think makes it particularly interesting as an opportunity for innovation, especially on the data science side. And DAS is a relatively new source of data for the geophysics community. And that means that we need some new algorithms, because although there's been a lot of development and algorithms have explored how to analyze data from traditional seismic instruments, there's been a lot less work about how to analyze DAS data. And so some of the existing methods that are out there for seismic data may not account for some of these properties that are specific to DAS. For instance, the data volume. Some of the existing algorithms may not be designed to scale to data volumes as large as we see with DAS data sets. They may not be designed for data they're often designed for purpose-built scientific sensors, and so the data quality of DAS may present a challenge for some of these algorithms. They may not transfer well. DAS also is taking different kinds of measurements than traditional seismic sensors. These are distributed versus point measurements. It's measuring strain, and there's directional sensitivity. So these kinds of differences between the measurements that DAS is taking versus traditional instruments need to be accounted for by new methods. And that includes the array geometries, which are flexible, since these are measuring along fiber. Fiber is a lot more flexible in terms of where it can go, and the geometries these arrays can take. Another aspect of DAS data being relatively new is that when we start thinking about the most powerful machine learning algorithms like deep learning, many of these are very data hungry. They require a lot of past labeled data in order to use these algorithms and take full advantage. But when you have a new data source like DAS, there's often not a lot of labeled data available. The data is often very large, but it's not well annotated and not well explored. And so there's a need to look into things like unsupervised methods, or methods called transfer learning, which allow you to take machine learning methods that have been developed using data from traditional instruments or DAS arrays potentially from other settings, and apply them more broadly to DAS data. So I think there's a lot of interesting opportunities here from the point of view of big data. And so although I've talked about these sort of challenges for DAS data, there's a lot of solutions out there as well. This isn't just a list of sort of problems and challenges. And over the last decade, there's really been an explosion of work in developing new algorithms for analyzing big data, along with improvements in computing technology and software that help make these algorithms both faster and easier to use. And so what kind of approaches are available to us for analyzing big data? There's several different approaches we can take. One is to use efficient algorithms. So these are algorithms that are designed to scale with your data volume. These algorithms might scale linearly or subquadratically, which means that as your data grows, the compute time doesn't increase faster or too much faster than the growth of your data set. And so that's what you really need in order to be able to apply methods to large data sets. As your data grows, you can't have the compute time growing too rapidly. So there's methods for this, efficient algorithms like randomized algorithms, which I'll talk about an example in a minute, streaming algorithms, and so on. So there are algorithms designed specifically to have these scalability properties. There's also a lot of interest in for big data sets, another set of solutions is automating the analysis with data-driven methods, like large-scale machine learning. And by large-scale machine learning, I mean machine learning methods that can be efficiently trained or applied to large data sets. For instance, deep learning methods, which can be trained using large data sets and then quickly applied to new data. And machine learning algorithms are often useful for analyzing big data because they often get better performance or are able to use computational resources more efficiently than alternative methods. Another approach for analyzing big data sets is using more compute, more computation. And so developing algorithms that can leverage parallel and distributed computing is also an important direction. Another approach for analyzing large data sets is to reduce the amount of data that you have, to do some sort of data reduction. This might be filtering the data, this might be compressing the data, reducing the dimensionality. And so this is a way of taking the big data sets and making them more manageable so that you can use algorithms that were not necessarily designed for the biggest data sets and apply them to these new data. And finally, in many cases, in order to really analyze big data, you may need custom or task-specific algorithms. Algorithms off the shelf developed for sort of general purpose tasks may not always work for your big data set. You may have to take advantage of the particular characteristics of the data or your problem in order to get your methods to scale. So these are all different kinds of strategies for dealing with big data. And so I'm gonna dig into a couple of these a little more. But first, I just want to mention that seismology isn't the only scientific discipline that's dealing with massive data sets. So outside of seismology, especially in other physical sciences, they also have extremely big data. So for instance, in particle physics, they have these large particle accelerators that generate, essentially they're generating too much data to even store. So one of these large experiments might generate 1 billion collisions per second, which corresponds to 1 petabyte of data per second, which is you can't store that much data. So in these kind of applications, one of the things they do is data reduction. They do data filtering. They don't even store all the data. They pick out which events are going to be the most interesting, a very small percentage of the actual events that are happening, and they store only that small subset for analysis. In another field, astronomy, there's a new project to build the world's largest radio telescope made of an array of many different receivers. And this is something that they're developing in an ongoing way. And this is another example where they essentially have too much data. So they have multiple processing steps in order to reduce the amount of data. And the way that they think about it in this application is with each processing step, they're reducing the size of the data, but in some sense increasing the information content, making that data, putting it into a form that's more useful for scientists to analyze and to look at. So they have some real-time processing of the raw data. They also have dedicated supercomputers that are processing the data. And in the end, they're generating these sort of science data products that aren't, rather than the raw data that they're sharing with the community, but these data sets are still enormous, up to 600 petabytes a year. So these are very large data sets, and they're using some of these techniques I mentioned, data reduction, real-time processing, and using supercomputing. But another direction that they've been moving towards recently is data-driven algorithms. For example, at the LHC, for these sort of particle accelerators, there's been a lot of work exploring using machine learning, one, to improve the data reduction, to improve filtering, make their use of data storage more efficient, and also then to classify events to help sift through the data that they are storing. And so this is an area that not only we're moving towards in the geosciences, but also in other sciences more broadly, is thinking about how can data-driven algorithms really help process these large data sets. And so I want to just talk a little bit more about machine learning as one of the examples of the tools. So machine learning algorithms, these are methods so machine learning is a subfield of AI, and these are, that uses methods that learn from experience. So the algorithms learn from experience, which for a computer, experience means data. So these are algorithms that are using data to both recognize complex patterns and build predictive models. And so this is something that sounds very abstract, but it's actually something that you've probably done before. So an example of this would be linear regression, where you have some data and you use the data to actually fit your model, which is going to be the best linear model that most closely follows the data that you've observed. Machine learning algorithms have two useful properties. One is that they have data-driven outcomes. So the model that you get is going to depend on the data that you've seen. That's true with linear regression. The line, the best fit line in this case, will depend on the data that you have available. And they also have, these methods have the ability to generalize. So you can apply and make predictions for data that the algorithm has not actually seen before. All right, so within machine learning, there's sort of two broad classes of machine learning methods. And the first is building models using examples. And this is what's called supervised learning. And this is has two stages. The first is the training stage, and then followed by the prediction stage. In the training stage, the idea is we want to build a model that can take some sort of data and map it to an output to make a prediction. So in order to build the model, we generate a list of examples of the pattern that we want. So say we want to build a model that tells you whether an image is a cat or a dog. We collect a number of images with labels about whether they're a cat or a dog. We pass these to our supervised learning algorithm. There's many of them out there. And the output that we get from the algorithm is actually going to be a model. It's a predictive model that we can feed new images, and it will give us the label that goes with them. So when in the prediction phase, we now take our model that we've trained, we can feed new data to it, and it will tell us which class the data belongs to. And it does this, it builds this model by finding an optimal formula to separate cats and dogs based on that training data. And that allows it to take new data and actually make a decision for those. And I just want to mention that, even though I'm showing this with sort of cats and dogs, this silly classification problem, you can do this with any kind of data. So you can think of mapping inputs to some sort of output you want to predict. That might be mapping raw DAS data to say some sort of a category of the event we're seeing in the data. It could be mapping data to a more high dimensional output, like a denoised version of the raw data. There's also another kind of machine learning method called unsupervised learning, which is about finding patterns in data. And this is potentially very applicable to DAS for the very reason that we may not always have these large labeled data sets to learn from. And so this is something that you can apply when you have data, but you don't actually have examples of a particular pattern you're trying to find. So in unsupervised learning, you have data without labels, you feed it to the unsupervised learning algorithm, and the output that you get is some sort of structure in the data. Now, the structure you find will depend on the algorithm you choose, but that might be a structure like common patterns or features in your data set. It might be groups of similar objects within the data, or it could be a model of the data itself, of the data distribution. And I don't have a lot of examples of machine learning in DAS. I know it's something that people are starting to apply to DAS data, but in terms of specific examples, if you're interested, I have a review paper that my co-authors and I published about a year ago that you can look for specific examples of how machine learning is being applied broadly within the geosciences. So that's sort of machine learning and one potential tool for dealing with these large data sets. And I do want to give you another specific example from my own work of how an efficient data-driven algorithm can be applied to large seismic data sets to allow us to scale up our analysis. And so this is a project that I worked on during my PhD that was focused on large T earthquake detection. So it's a little bit different kind of big data at Stanford with Clara Yoon, Greg Broza, and others. And so then this project, we wanted to leverage algorithms that were used for efficient audio recognition to be able to scale up earthquake detection in large, long duration data sets. The idea was we wanted to be able to discover new event waveforms without actually having labels. So it's in this sort of unsupervised framework. And we were able to find 1 to 2 orders of magnitude more earthquakes using this approach. And then we wanted it to be able to scale up. So in the end, we were able to process 500 times as much data with a reduced runtime compared to our sort of initial naive approach. And so I just want to give you sort of a flavor of how this works. I don't have time to go into all of the details, but FAST takes a data mining approach to analyzing big data sets. So data mining is methods for extracting patterns from large data sets. And the pattern that we wanted to extract were repeating or similar waveforms. And the reason for this is waveforms are known to repeat. This is sort of the principle behind template matching, which is a popular technique for earthquake detection. And so we want to do template matching without templates. We want to do template discovery, looking for repeating patterns in these long duration data sets. Now, doing this in a naive way, doing an exact search where we break up our data into little pieces and compare all of these sections to find any that repeat, that's not going to be efficient. It scales quadratically with data duration, and so you can only apply this to very, very small data sets. So instead, what we want to do is think about how can we scale this to big data sets. And so for that, we use a technique called locality-sensitive hashing, which is designed to find similar items in large data sets. So it's developed for applications like finding duplicate web pages. It's also been applied to problems like searching for copyright content or plagiarism. And also it's been applied to identify songs in apps like Shazam. So this is the kind of tool that we want to take that have been developed by the tech industry for scaling to big data sets, finding similar items, and apply it to our seismic data set. And so without going into all the details of how LSH works and why it scales, I just want to give you sort of an overview of what makes it scale. So the idea behind LSH is that if you're searching a well-organized data collection, it's going to be much faster than searching a disorganized one. So this method, locality-sensitive hashing, is essentially clustering together similar waveforms in a database that allows us to quickly retrieve the ones that we want. And where the speed up comes from is that what we're sacrificing a little bit of accuracy. And what I mean by a little bit of accuracy is a guarantee of success in our search. And in exchange for that, we get a significantly reduced runtime. So FAST is using an approximate search that's able to run quickly rather than a slow exact search, which will be perfect every time, but it's going to take a long time to run. So we get this trade-off. This is common in a lot of these big data techniques, is you might trade off a little bit of accuracy for an increase in computational performance. And so doing this, we were able to extend what was initially an exact search approach, which we could run on 7 days of data and took about 200 hours, which was extremely slow. We couldn't scale this up. To eventually we got fast running on 10 hours of data, and it would, 10 years of data, and it only took a few hours to run. And so even though this is sort of long, large T data, rather than the large N framework that we think about with DAS, I think the ideas behind FAST, this idea of using efficient methods that have been developed from other fields, and being able to apply them to seismic data, I think is going to be useful moving forward. So just to conclude, DAS is producing much larger and more complex data sets than a lot of the other traditional seismic arrays. And there are a lot of solutions out there from modern data science and computing, including machine learning methods, these computationally efficient algorithms, and then other techniques like parallel distributed computing, data reduction, and so on. So I'm happy to take questions. And also I just wanted to mention that just because the sort of webinar interface is a little bit awkward and hard to sort of have discussions, after the workshop is over today, I'll be on Zoom. You can just drop in if you want to sort of chat. I'll sort of have an open office hour for anyone who's interested. And I'll put this Zoom link also on the Slack for anyone who's interested. So thanks, and I'm happy to take questions.
Thank you, Karianne. Thank you. That was very, very interesting. We have at least a couple of questions, the open questions in the question and answering session. So, Matthias Omberger asked regarding the data reduction problem. If data is reduced while recording, would one eventually fail to find surprising new things in the data? So, if we downsampling, are we concerned about losing data may be important 10 years from now when we have new techniques?
Yeah, so that's a really good question. I do think that is one of the big challenges with the data reduction strategy, is that in some sense, especially if you're, there's a couple ways of doing this. Some are using rule-based systems. So that's currently how the LHC system works right now, is they're using like a rule-based system where they have these sort of ideas about what kind of signals might be interesting, and they want to move to machine learning. But in both of these settings, you do have the possibility that you're going to potentially throw out something interesting. And so that is, I think, from a data science perspective, a really challenging and interesting problem of how do you sort of account for novelty or, these surprising cases. And so it is something that I think you have to design into the system, but it is definitely a risk in those cases. But in another sense is, what else do you do if you're generating a petabyte per second? There's no way that you're guaranteed that you're going to find every single interesting signal in there. It's just too much data. So in some sense, you also have to do the best that you can. But I think that there's a lot of room to design the sort of novelty, looking for novelty into the algorithms that we're developing.
So another question, Dominique Eslamian is asking, what would be the minimum threshold for the amount of time or channels needed to train a neural network. So we are collecting, thousands of channels. How much is the minimum time? Will that be depending on the event that we are looking for?
Yeah, so it's really going to depend a lot on what you're looking for. So if you're trying to, right now there's neural networks. There's a whole host of different kinds of neural networks. So there's a lot of the really powerful supervised methods, neural networks or supervised methods. There's also unsupervised neural networks as well. But in all of those cases, you do at least need a fairly large data set. So I don't know. I think if you're trying to find specific events, you are going to need some reasonable number of examples. And again, that's specific on a number of factors, including how complicated the patterns of the signals that you're looking for. If you're looking to find something that's, not a particularly challenging signal to pick out, you may not need as many examples as something that's more subtle. But for most neural networks, I would say you usually would need minimum on the order of thousands, maybe tens of thousands of examples. It really depends.
So another question would be, so far is the presentation was what you data scientists can do for us. Mm-hmm. But the other would be how we can collect data in a way that will benefit your application. When we do the design of data collection, what we should do differently to be able to help apply your approaches?
Yeah, so I think from the perspective, I guess so it sounds like the question I'm interpreting this is kind of what can scientists do to help data scientists make it easier to work with the data? And I think one of the things is that can be challenging is just figuring out what the data is and what an interesting thing to look for in the data would be. Like, what are the interesting questions to ask with the data, and also to have some of the context of the data. So having good, I would say, metadata to go along with it that explains what the data is and what would be interesting to find. Because I think it's easy to find, a data set and then, do some analysis that's not actually helpful or interesting, or for there to be some maybe pre-processing that was applied that you didn't know about that affects your results. And so, but I think for a lot of these kind of data sets, it's really important also to be able to work together. And so I think in some cases, approaching data scientists directly and trying to form a collaboration can be useful, because I think it is hard to just, go approach a data set where you don't actually have an expert to tell you anything about the data, and then do something useful. Like, you really need to have experts on both the science side and the data side, I think, working together.
Thank you. So I'm going to take the opportunity that Nate Lindsey is on the call, and he can ask the question that he posted by himself. So Nate, if you want to unmute your mic.
Yeah, thanks, Karianne, for the great talk, the great perspective here. And while there's more questions probably coming in, I wanted to just ask about this paper by Matsuya Reisi at Brown, looking at like physics-informed deep learning, and so and how that, I mean, it's been applied in kind of fluid mechanics to look at kind of a deep learning framework based on some physical equations. I was wondering if you could kind of speculate. I don't think it's been applied to DAS yet, but how that might be applied in the future to DAS, and what kind of steps would be required to kind of bring that type of learning method to DAS data.
Yeah, so that's an area that I'm really interested in, is thinking about how do you bring in these other sort of domain knowledge, physics, or models into these data-driven methods, because I think you do need, in many cases, a hybrid, and that can reduce the amount of data that you need for learning, is if you have sort of physics to act as a regularizer to sort of limit the search space and sort of direct you to the right solution. If you have prior information, you don't need as much data to get you there. For DAS, it's hard for me to say, because I'm really new to DAS. I don't know a lot, as much about it. So it's hard for me to say, where bringing in the physics might be useful. But I do think that this is something that that broadly would. I mean, there's a lot of ways aside from just physics directly, but other kinds of domain knowledge. And so this is something that we saw, for instance, with FAST, we see this, where the domain knowledge we're bringing into it is that we're looking for repeating signals. That's not something that, you would have to know that a repeating signal was interesting and that's coming from our domain expertise. And so that's something that's sort of built into the system. And so there's a lot of ways of bringing this knowledge in. These sort of physics informed methods are usually bringing in sort of specific like differential equations. And so I don't know where we would see that with DAS specifically. But I would definitely be, open to chatting more about that if people are interested. I think it's a really interesting topic for sure.
Yeah, it seems like there's a real opportunity because a lot of the arrays that are deployed for DAS, they're recording at many different frequencies, and it's really hard to kind of get a sense of what physics are actually, being applied or being recorded. So if there were kind of methods that could go out and search for, oh, that looks like wind, or that looks like, wave propagation in shallow water.
Yeah.
That looks like an earthquake wave. This could be really useful for DAS.
Yeah, and there has been work in the machine learning community trying to look at data and actually discover like what are the physics that are governing what we're seeing. And so, and I think that's closely related to the paper that you mentioned. And so there is this idea of kind of physics discovery with machine learning that, especially I come from an applied math background, so that's something the applied math community is very interested in. And so for those kind of signals, like it could be interesting to see, what could we pull out those specific sort of dynamics or separate things in that way. And I do think that, when you talk about the geometry of DAS, like that's another kind of information that you could try to bring in and encode in some way in these solutions, rather than having the methods kind of have to discover something that, discover patterns that are based on this network geometry. If you could give it information about that, it could be helpful as well. So.
Great, thanks.
So Karianne, you talk about different type of approaches in which you reduce the precision of your data analysis to be able to minimize the speed of the algorithm. So what order of magnitudes are we talking about? So one of the things that we are very concerned is about arrival time. So will be a reduction of 10% in the precision of arrival time. Do you have any order of magnitudes when first to those type of algorithms?
So for a lot of these algorithms, especially like the efficient algorithms or randomized algorithms like the locality sensitive hashing, a lot of those have a mathematical theory behind it that actually can tell you sort of what are the bounds on the accuracy loss. So for a method like with FAST, when we're using LSH, we're essentially getting a very, very small percentage. Like you have a small chance of getting missing a detection or getting a false positive, but that might be less than 0.001%. And this is something you can actually control with the parameters of the algorithm. And so a lot of these algorithms do come with these kind of bounds, a theory that goes with it. In other cases with other methods, like in machine learning, usually you don't have good sort of control error bounds on these sort of things. So it depends a lot on what method you're using and whether or not you can sort of put that mathematical theory behind it, and actually if that's something you can control. And that's one of the limitations of machine learning, is that it is hard to put sort of an error bar on what you're getting. And there is interest in that with these sort of Bayesian approaches to put uncertainty estimates on things, but it is hard to know how accurate those things are going to be in some cases.
So Karianne, I hope that you are taking notes about the location of the data that we have available, because we will need your help. Data, and we are just scratching the surface, and we need to get experts in your area to be able to help us dig much more into the data and the phenomena that we are evaluating. Yeah, I don't know if there is any more question from the panelists. If not, I will pass the torch to Scott. And Karianne, thank you very much. It was a very, very interesting.
Thank you, Karianne. Thank you, Dante.